Good morning, everyone, and welcome to this lecture. This is lecture number 1 in nuclear physics, and we are going to deal with nucleus in this chapter. So, nuclear physics is a branch of you can call modern physics, or you can call it as a branch of physics which deals with the study of nucleus. Here, we are going to study nucleus and what happens inside a nucleus. Do we understand this?
Yes, sir.
Now, as soon as we get into nucleus, as soon as we get into nucleus, we must understand what is a nucleus and what it all consists of. Anyone remembers nucleus in the experiment carried by Rutherford? Was
Yes,
that Rutherford? Scattering experiment. He found out that most of the mass of the atom is concentrated in a very small space at the center, and he called that space as the nucleus. Yes or no?
yes, sir.
This nucleus basically consists of two particles which were discovered by Chadwick and Goldstein. Chadwick discovered neutron. Neutral particle does not have a charge. Goldstein discovered proton, charge equal to the charge of an electron but positive, and mass, as you can see, their mass are almost same. Yes or no?
Yes, sir.
Mass of a proton is slightly, very slightly less than the mass of a neutron. Otherwise, their mass are exactly equal. Neutrons and protons together, they are known as nucleons. Do we know this? Yes or no?
Yes, sir.
The mass of electron. Where does electron come here? The mass of an electron is very, very less compared to the mass of a proton or compared to the mass of an electron. In fact, the mass of the proton is approximately how much times? Mass of the proton is approximately equal to 1800 and 40 times the mass of an electron, and mass of a proton is approximately equal to mass of a neutron. So in many cases, some cases, we can not in this chapter but the chapter before, we sometimes neglect the mass of an electron as compared to the mass of a proton. But in this chapter, we cannot do that. In this chapter, we are going to deal with nuclear physics. So this electron should not come. If electron comes somewhere, we'll have to understand that this electron also has a mass. Do we understand this?
Yes, sir.
These are values. You may not remember these values, but you will be using these values, and you might encounter questions where you will have these values. So this is electron, proton, and so on. And then how do you represent an element or an atom? How do you represent an element or an atom? How do you represent an element or an atom? So here you can represent the nucleus of that atom. And how do you represent this? This X stands for the symbol of the atom: hydrogen, helium, H, He, oxygen, O, carbon, C, nitrogen, N. Do we understand this?
Yes, sir.
Z stands for Z, stands for the atomic number. Remember, atomic number is always the number of protons and not the number of electrons. Number of electrons can be changed. An atom can gain or accept electrons, but that does not change the type of the atom it is. Only by changing the number of protons, we can change the atom by changing its nucleus. Do you understand this?
Yes, sir.
Then the third thing is atomic mass number or mass number. I hope you know this mass number. Yes or no?
Yes, sir.
This is the total number of nucleons, which is the number of protons plus the number of neutrons. Everyone understands this?
Yes, sir.
You will have to note this down. I'll give you 2 minutes to do it. That takes us to the next heading. And in this next thing, we see an important note. You can just note it. If you have a free neutron outside the nucleus, it cannot exist as a neutron. It will break into a proton, an electron, and it will give out a particle which is known as anti-neutrino. This is the symbol of anti-neutrino. Remember, this 1H1 represents a hydrogen nucleus. A hydrogen nucleus only consists of one proton. So 1H1 is actually the symbol of a proton. You can also use it as proton. Do you understand this?
Yes, sir.
Then atomic mass number, or sometimes you may not call it an atomic mass number, you call it an atomic mass. Atomic mass number, I hope you know this. This is the nearest integral value of mass of the element or the atom or the nucleus, which is represented in atomic mass units, AMU, or you call it AU these days. AU or MU? AU. One AMU or one AU is 1 by 12 the mass of one atom of C16. C12, do we understand this?
Yes, sir.
The value of one AMU is this much. We all know this.
Yes, sir.
Now remember that by Einstein's equation, E is equal to mc square mass into c square. Yes or no?
Yes, sir.
One AMU mass is approximately equal to 931 point, I think, 5 mega electron volt. So remember this conversion of AMU into energy. If you have a mass of 1 AMU, that is actually energy. That mass can be converted into energy by this equation, which is approximately given here. So that is why it is written as 1 AMU is 931.478 mega electron volt per C square, and that is why it is written in that fashion. So remember this, 1 AMU is 931.5 mega electron volt. I'll give you 2 minutes to note this down. Then we have these three things that you might be aware of. The first one is isotope. Isotope are nucleus or atoms which are having same atomic number. As soon as we say same atomic number or same number of proton, that means the nucleus remains same. But they have different mass numbers. So they have different number of neutrons. So they will be representing the same element. Do we see this? These are three isotopes of hydrogen over here. These are three isotopes of oxygen written over here. These are two isotopes of helium. They have the same atomic number. That means they are from the same element, same atom, but different number of neutrons. Do we understand this?
Yes, sir.
Then comes isotone. What are isotone? They have the same number of neutrons, but different atomic numbers. So you just reverse it. Atomic number means the number of protons. If number of protons is same, it is isobar. If the number of neutrons is same, then they are isotones. The value of A minus Z Number of neutrons is same. Do we see this? One is beryllium, other one is boron. Please listen to me. One is carbon, other one is nitrogen. Different elements. One is fluorine, the other one is lithium. Do we see this?
Yes, sir.
Oh, sorry, not here. The one is oxygen, the other one is fluorine. Do we see this? Same number of neutrons. We understand this?
Yes, sir.
The third one is isobars. They have the same mass number. You can see same mass number. When I say mass number, I mean what? I mean the same number A. Do we understand this? A is same, Z is different. Do we understand this?
Yes, sir.
That is how I remember it. Isobar, same number of proton. Isotone, same number of neutrons. Isobars, same mass number. Proton, neutron, mass number. Proton, neutron, mass number. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note this down. Well, the next heading is the heading of size of nucleus. Now, the size of the nucleus is in the order of 10 raised to the power minus 15 meters, which is known as Fermi meter. Very small. Now, radius of a nucleus is given by this formula R is equal to R naught A raised to the power 1 by 3, where R naught is a constant, empirical constant, and the value of R naught is 1.1 Fermi meter. A is the atomic mass number of the atom. Heavier nuclei, heavy nucleus, more mass, more atomic number, so more is going to be their size. Do we understand this?
Yes, sir.
If we talk about the volume of the nucleus, assuming it to be spherical in shape, you will see that this volume of the nucleus will be coming directly proportional to the atomic number, a very important result. Do we understand this?
Yes.
But once we talk about the density of the nucleus, the density of the nucleus, which is nothing but mass divided by volume, and when you put all these values, you will see that the density of any nucleus, whether it is a nucleus of hydrogen or carbon or nitrogen, whatever is coming in this formula is independent of the atomic number or the mass number. Do we see this?
Yes, sir.
That means nuclei of almost all atoms have almost the same density. We understand this?
Yes, sir.
The density of the nucleus is maximum at its center, and as we move away from the center of the nucleus, the density is less. I'll give you 2 minutes to note this down. Then you have to find out this one. Find the ratio of radii of nucleus of aluminium 27, 13, and beryllium 1, 25, 52.
Sir, it is option A.
It is option A. You must remember that this radius of nucleus is equal to R naught into A raised to the power 1 by 3, where R naught is 1.1, approximately 1.1 Fermi. Yes or no?
Yes.
That's it, my dear friends. So, radius of aluminium divided by radius of beryllium will be equal to 27 by 125 raised to the power of 1 by 3. I think this is going to come as 3 by 5. 3 by 5 is same as 6 by 10. Do we understand this?
Yes, sir.
Everyone understands this.
Yes, sir.
This is the next question, my dear friends. And if you're lucky, the same question may appear in your exam. 2 copper 64 nuclei touch each other. The electrostatic repulsive energy of the system is. Here the value of R naught is not given, my dear friends. R naught can be taken as 1.2 for me. 1.2 for me. How will you do this problem? I'll give you 2 minutes to think about it. Let me help you out in solving this question, then I'll give you one more to solve this. How are you going to do this? First of all, if you imagine that these are the two nuclei of this, you will have to find out the center to center distance between them. Yes or no?
Yes, sir.
That center to center distance between them would be equal to 2r. Yes or no?
Yes, sir.
The value of r is given by r naught into a, which is the mass number raised to the power 1 by 3. Yes or no?
Yes, sir.
In this case, what will be the value of this r? R naught is given as 1.2. The mass number of copper is 64 raised to the power 1 by 3. So I think it will come as 4.8 for me. Yes or no?
Yes, sir.
To find out the electrostatic potential energy of this system, that will be equal to K into Q1 into Q2 divided by the distance between the center R square. Yes or no? Not R square. It should be K Q1 Q2 by R. Remember?
Yes,
Electrostatic potential energy of two spheres or 2-point charges. What is the value of K? 9 into 10 raised to the power 9. Yes or no?
yes, sir.
Now you must find out both the nucleus have the same charge. What is the charge on that nucleus? That charge on the nucleus will be equal to the atomic number of copper. What is the atomic number of copper? Well done. At this point in time, I have to tell you the atomic number of copper.
29, sir. Sorry.
God exists. I always start questioning the existence of God, but then I come to know that God exists. So 1.6 into 10 raised to the power minus 19 coulombs is the charge of one electron, and it has 29 electrons taken apart. So Q square divided by 2 into the radius is 4.8 for me. 4.8 into 10 raised to the power of minus 15. That would be the energy in 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 joules, but the answer is given in mega electron volts. 1 joule and mega electron volts. You know, 1 mega electron volt is 1.6 into 10 raised to the power minus 19 joules. So joule will be divided by, so it will be divided by 1.6 into 10 raised to the power minus 19. I don't understand that it's a very difficult calculation for you, but I can't make it any more simpler. The answer that is given to me is 126.15 mega electron volts, and that is the answer that I am going to present to you. And if this question comes ever, ever, this is how you need to do this. Do we understand this?
Yes, sir.
I'll give you 2 minutes to take a deep breath, close your eyes, absorb it, open it, see it, note it, and if possible, remember it. Then comes this pretty simple question. Uranium U-23592 undergoes fission. What is fission? We'll come to that. How it happens, we come to that. Let us now concentrate on the problem that we have in hand. 0.1% of its original mass is changed into energy. How much energy is released if 1 kg, 1 kg, 1 kg, 1 kg of uranium U-232, 23592 undergoes fission? I give you a minute to do this. So, how are you supposed to do this? Initially, you have 1 kg of uranium U-235. 0.1% of the mass is converted. Energy into mass is mass into C square. So how much energy I will get? How much mass is converted? 0.1% of 1 kg. That is the mass multiplied by C square. C is 10 raised to the power 8. 3 into 10 raised to the power 8 square. You multiply and you divide. And the answer that I have is option D, 9 into 10 raised to the power 13 joules. That is the answer we were supposed to get. Do we understand how this is done?
Yes.
Everyone understands this?
Yes, sir.
Then I'll give you, have you noted this down?
Yes, sir.
Then I'll give you one more so that you can get the answer and then stay happy. 1 gram of hydrogen is converted into 0.993 gram of helium in a thermonuclear reaction. How it's happening is none of our concern. You just have to find out how much energy is released. So 1 gram of hydrogen and you have 0.993 gram of helium. The rest of the mass has disappeared. So that mass which has disappeared, let me call it as change in mass delta M. How much is the mass that has disappeared? That mass must have been converted into energy. How much mass? 0.0007 grams. That means 0.007 into 10 raised to the power minus 3 kg. This much of mass. Total mass was 1 gram. But at the end, I get 0.993 grams. That means some mass has been lost. This mass is sometimes known as the mass defect. We'll see what is mass defect. So this much mass has gone. This much mass would have been converted into energy. How much energy I will get? This mass which has been converted. In the first question that we did before that, it was given how much mass was converted. Directly it was given how much mass was converted into energy. In this question, it is not given directly, it is given indirectly. We had 1 gram of hydrogen and we have 0.993 gram of helium. How much mass has been converted? 0.007 grams of mass has been converted. Delta M into C square will give me the energy. C is 3 into 10 raised to the power 8. Once you multiply them, you should be getting your answer, and the answer that I have is 63 into 10 raised to the power 10 joules. I'll give you 2 minutes to note this down. The next heading is mass defect. What is this mass defect? Yes. What is this mass defect? Anyone? Any idea?
Change in mass.
Yeah, you can call it as a change in mass. Now, whenever this nucleus is formed for any element or any atom, it has been observed. What has been observed? Whenever a nucleus is formed, it has been observed that the mass of the nucleus is always less than the sum of masses of its constituent nucleons. That means the total mass of the nucleus is always less than the total mass of the nucleons which are making the nucleus. This difference in masses is known as the what?
Mass defect.
Mass defect. So mass defect is sum of the mass of the nucleus minus the mass sum of the mass of the nucleons minus the mass of the actual nucleus. Do we understand this?
Yes.
So it will be equal to Z times the mass of protons plus A minus Z times the mass of the nucleons. Do we understand this?
Yes, sir.
Z is the number of protons. A minus Z would be the number of neutrons. Yes or no?
Yes, sir.
So this would be the mass defect. This would be the mass defect. You can write this mass defect in this way if you want to write it in this way. It is the difference between the expected mass and the actual mass of the nucleus. What do you mean by the expected mass and the actual mass? The expected mass is the mass of protons plus the mass of neutrons. That is the expected mass. This mass should be the mass of the nucleus, but the actual mass of the nucleus actually comes a bit less. To find out the mass of the nucleus, how do you find out the mass of the nucleus? You subtract the mass of the electrons from the mass of the atom. Yes or no?
Yes, sir.
This is another way of doing the same thing. Do we understand this?
Yes, sir.
So you can write this in this fashion also. You can write this in this fashion also. Both of them mean the same thing. Doesn't matter. So the observed mass is less than the expected mass. The mass defect will be expected mass minus observed mass. Z times the mass of proton plus A minus Z times the mass of the neutrons minus the mass of the nucleus. Here I have written M. This M is actually I have written is at the mass of the nucleus. How do you find out the mass of the nucleus? You subtract the mass of the electron from the mass of the atom. Do we understand this?
Yes, sir.
Yes or no?
Yes, sir.
I'll give you 2 minutes to note this down. The next heading, and sometimes they're asking it, is known as the packing fraction. It's just a term that you must remember. This is the mass defect per nucleon. Do you understand?
Yes.
Mass defect divided by the mass number will give you packing fraction, and this is how the graph looks like. Packing fraction gives us the measure of stability of the nucleus. Remember, smaller the value of packing fraction, larger is the stability of the nucleus. Packing fraction may be positive or negative or even zero. At A is equal to 16, mass number is equal to 16 here, and at here 240, the packing fraction is 0. The mass defect is 0. Do we understand this?
Yes, sir.
Give you 2 minutes to note this down. Since we have talked about the stability of the nucleus, and this entire chapter is about the stability of the nucleus, we may now encounter a term known as binding energy, BE. Now, there are different ways in which you can understand this. You just need to understand it. The first way is we have seen that the mass of the nucleus is smaller than the actual mass of the nucleons put together. Yes or no?
Yes, sir.
That means when the nucleons they come together to form the nucleus, some amount of energy is liberated. This much amount of energy has to be given to the nucleus to break it up into its constituent nucleons. That energy is known as the binding energy. Do we understand this?
Yes, sir.
You can understand it in this way, or you can understand it in this way, that it is equal to the energy which comes because of the mass defect of the nucleus. There is a mass defect in the nucleus. The mass of the nucleus is less than the mass of the nucleons. Some amount of energy is liberated. That energy is known as the binding energy. So how do you find out the binding energy of the nucleus? You multiply the mass defect by c square. Yes or no?
Yes, sir.
So this becomes your equation where A becomes, remember, A is the mass of the nucleus. Do we understand this?
Yes, sir.
You will get this binding energy in joules if you write the mass defect in kgs. If you write the mass defects in AMU, what you can do, if you have the mass defect in AMU, you simply multiply this mass defect by 931.5 and you will get your energy in mega electron volts. Yes or no?
Yes, sir.
Because one AMU mass defect is 931.5 mega electron volts. So it's always better to express the mass defect in AMU, because then you can simply multiply it by 931.5 and get your answer in mega electron volts. Everyone understands this?
Yes, sir.
I'll give you 2 minutes to note this down. So just to make a point for you to understand, if you take the formation of oxygen nucleus, it consists of 8 protons and 8 neutrons. When 8 protons and 8 neutrons become the oxygen nucleus, the mass decreases and they release energy. That energy which is released is known as the binding energy, delta M into C square. Do we understand this?
Yes, sir.
Similarly, if you have to break this nucleus into its constituents, you have to break this nucleus and get nucleons out of them. Energy has to be supplied. They will absorb energy. That energy will be equal to the binding energy. Do we understand this?
Yes, sir.
Everyone understands this? So you want to note this down, or you have understood this? This is just for your understanding. Do you understand this?
Yes, sir.
Now, it may come to us that this binding energy is going to be a factor that determines how stable is the nucleus. That is not exactly correct. The factor that determines which nucleus is stable is given by binding energy per nucleon. Binding energy divided by the mass number is known as binding energy per nucleon, and this binding energy per nucleon tells us how stable is the nucleus. If binding energy of nucleus A divided by the mass number of nucleus A is greater than binding energy of nucleus 2 divided by the mass number of nucleus 2, that means the binding energy per nucleon is greater for nucleus A, then nucleus A would be more stable than nucleus B. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note this down. What do we see here is the binding energy curve. No, not exactly binding energy curve. Binding energy per nucleon curve. You may not draw this diagram, but you have to understand that this binding energy per nucleon, this is how it varies. This blue zone that you see is the zone between iron 56 to nickel 62. Iron 56 to nickel 62. Nickel 62 lies somewhere here. Nickel 62. This is the zone in which the binding energy per nucleon is very, very high. Is the highest. Is somewhere in the range of 8.8 mega electron volt. This is the region, the blue region, in which you find the most stable nucleus. So the most stable nucleus lie from iron 56 to nickel 62. Now, as you go to the right of this, the nuclear become unstable. As you go to the left of this, again the nuclear become unstable. Now, when a nucleus is unstable, it will try to come to a state of stability. Do we understand this?
Yes, sir.
That is what this entire chapter is all about. This is a very precise diagram. If you want to draw a simpler one, this is how a simpler one would look like. This is a very precise diagram that I showed you. I will show you a simpler version of it. Simpler version, let me first make it a bit smaller so that the simpler version fits. Let me make it a smaller one so that a simpler version fits. So this, on the right hand side, you see a simpler version of this diagram, which might be easier for you to draw. It's not very precise, but it just gives you a hint of what is happening. So I'll just give you 5 minutes to draw the simpler version. You may also draw that blue line if you want to. Then I will give you some important points. Well, then these are the final points of that curve. We can see the average binding energy rises very sharply, and then it becomes almost constant for a very broad range, and then it dips. Do we see this?
Yes, sir.
Higher the bonding energy per nucleus, greater is the stability of the nucleus. We understand this?
Yes,
Most of the stable nuclei will have binding energy somewhere between 8 to 8.8. 8.8 is the most stable, which lies somewhere between iron and nickel. Yes or no?
yes,
Most of the elements which are stable, the binding energy, the large part of the curve is flatter and it lies somewhere between 8 to 8.5. Yes or no?
yes, sir.
At elements with mass number less than 25 have low binding energy per nucleon, so they will combine together and form bigger nucleus so that they become more stable. Do we understand this?
Yes, sir.
You want to note this down?
Yes,
Note it down fast. Then again, you don't have to remember everything. You just have to remember less than 25 what happens and more than 220 what happens. Between 25 to 65, the mass number the binding energy per nucleon steadily decreases, and it becomes more stable at between iron to nickel. Therefore, the iron, copper, and nickel form the core of Earth. From 65 to 160, it remains almost constant. Beyond 60, it becomes 8. With more than 220, it becomes less than 8, and they become very unstable. And they have a tendency for fission. I just showed you that formula, right? I just showed you that diagram. Less than 25, they try to go to fusion. More than 220, they go for fission. So between the range from 8 to 8.5, you have the most stable nuclei. Do we understand this?
Yes.
So we have seen that right from the chapter on potential energy, work power energy, we have been seeing that everyone wants to come to a state of maximum stability. Maximum stability means minimum energy and you are more stable. Yes or no?
Yes.
So this nucleus would also want to become more stable, and the most stable nucleus lie in the range from 8 to 8.5 or 8.8 mega electron volt. Now, when you see that when the mass number becomes greater than 220, the binding energy per nucleon decreases. So if you have a heavier nucleus more than 220, if its mass number is, it will try to break into smaller nuclei or lighter nuclei so that it becomes more stable. Yes or no?
Yes.
That process, a large amount of energy would be released because the binding energy per nucleon of the product is more than the binding energy per nucleon of the reactant. That is why it is getting converted. It is breaking up into smaller particles. This type of nuclear reaction is known as nuclear fission. Do we understand this?
Yes.
This will only happen when the mass number is greater than 220. If the mass number is less than 25, then you can see the lighter nuclei will try to combine together to become a heavier nucleus because the heavier nucleus is more stable than the lighter one. Yes or no?
Yes.
Again, in this process, energy would be released. This process will be known as nuclear fusion. Do we understand this?
Yes.
In both these processes, the products are more stable in compared to reactants, and Q value of this thing is positive. What is Q value? We will come to that. Right now, just note this down. Do we understand this?
Yes.
I'll give you 2 minutes to give me the answer, to note this down. This is a question given. Following data is available about two nuclei, P, Q, and R. Arrange them in decreasing order of their stability. I'll give you a minute. So, how are we supposed to find this? We have to find out the binding energy per nucleon. For P, it is binding energy per nucleon is 10. Here it is 12, and here it is 11. So Q, the stability of Q will be greater than the stability of R, will be greater than the stability of P. P is the less stable, though it has the greatest binding energy. Do we understand this?
Yes.
Yes or no? No, yes.
Yes.
Everyone understands this.
Yes.
Then we come to the next heading, and the next heading, just give me a minute. Then we come to the next heading, and the next heading is nuclear reaction or nuclear collision. So you can write the next heading, nuclear reaction or nuclear collision. nuclear reaction or nuclear collision? Have you heard the term nuclear reaction or nuclear collision?
Yes.
What do you mean by nuclear reaction or nuclear collision? Yes, nuclear reaction or nuclear collision. What we are going to see is a nucleus. As you can see, if the mass number is more than 220 or less than 25, it will either break, or two lighter nuclei will make a heavier nucleus. In most of the cases, what is going to happen, that is their spontaneous breaking up. We'll come to that. But let us first deal with this. You will have a parent nucleus X, and in most of the cases, this might be at rest. This parent nucleus would be at rest in most of the cases. A nucleus would be at rest, and then there would be a particle which will be bombarding it. Boom. Do you see that particle here?
Yes, sir.
Where is that particle? That particle is the particle A incident, which in most of the cases would be moving. Now, whenever you have this, you might have in between, you might have a compound nucleus, which may not come, and this compound nucleus, because of this bombardment, will break up finally into a daughter nucleus Y, some more product apart from the daughter nucleus, and some amount of energy is liberated. Here X and A are known as reactants, and Y and B are known as products. This reaction is known as AB reaction. A is converted into B and is represented by X, A, B, Y. So X is bombarded with A, and at the end we have Y and B. Do we understand this?
Yes.
This is how nuclear reactions happen. This is how nuclear reaction happen. Now, in most of this nuclear reaction, there would be three equations that we need to apply, or three principles that we need to apply. The first principle that we need to apply is, you may not apply it, I will just give you the shortcuts for this. A question from this section came in JEE Advanced of last year. The first principle that we might have to apply, I will not be applying it, I will just give you the formula: conservation of momentum, because this is nothing but particles colliding. The second principle that we have to apply is conservation of charge. Charge has to be conserved. Yes or no?
Yes, sir.
The third principle you have to apply always, and in this case, mass is getting converted into energy, so the conservation of mass and energy. Do we understand this?
Yes, sir.
Now, any nuclear reaction? Okay. I'll just finish here so that I can have some space in the later half. I'll give you 2 minutes to note this down up till here. Everyone understands this?
Yes.
Okay. Now let us move ahead and see this reaction in detail, and I hope that you don't get confused. So do it slowly and don't get confused. If you have any confusion, you can ask me. I'll go slowly. If you are not confused, then that means it is good. Now, if in general I take any nuclear reaction, A plus X will give you Y plus B. A may be some nucleus, sorry, X may be some nucleus, A may be some particle which is bombarding it, Y may be the daughter nucleus, and B is the product that is formed. Yes or no?
Yes.
Do you understand what is this Ka, K1, K2, K3 and K4? Do we understand what is this K1, K2, K3, K4? This K1, K2, K3 and K4 are the kinetic energies of these bodies. Kinetic energy of A, kinetic energy of B, kinetic energy of X, and kinetic energy of Y. Do we understand this?
Yes, sir.
Now, if I apply the mass energy conservation equation by mass conservation, my mass energy by mass energy conservation equation, K1 plus K2 plus mass of A plus mass of X into C square, that should be equal to K3 plus K4 plus mass of Y plus mass of B ka C square. Here mass is converted into energy and then we have kinetic energy. Yes or no?
Yes, sir.
Everyone understands this? Yes or no?
Yes, sir.
Now, now, if I can write a term Q, if I can write a term Q, can write the term Q like this. I can write the term Q as MA mass of A plus mass of X minus mass of Y plus mass of B into C square. That means this is nothing but summation of mass of reactants minus summation of mass of products into C square. This Q, this factor Q is known as the Q value of this reaction, and this Q value of this reaction basically tells us the energy absorbed or released in this reaction. This gives us the energy absorbed or released in the reaction. Do we understand this?
Yes.
So now I can write equation number 2 in this fashion. Okay, I should use the same color. Equation number 2 like this: K1 plus K2, K1 plus K2 plus Q will be equal to K3 plus K4. Yes or no?
Yes.
This Q is known as the Q factor. This Q factor, and from here you can write the value of this Q factor as summation of kinetic energy of the products minus summation of kinetic energy of the reactants, which is nothing but equal to mass of the reactants minus summation of mass of the products into C square. Yes or no?
Yes, sir.
Do we understand this?
Yes, sir.
You can write the heading as Q value. I'll give you 2 minutes to note this down. Here also, please note one thing. If you apply the law of conservation, if you apply the law of conservation of momentum, let me apply it also. Law of conservation of momentum. If I apply the law of conservation of momentum, remember vectorly momentum of A plus vectorly the momentum of X must be equal to vectorly the momentum of P plus vectorly the momentum of Y. Do we understand this? This
Yes,
equation, the third equation, is a vector equation, so it has to be satisfied vectorly. We understand this? Yes or no? No or yes?
yes, sir.
I'll give you 2 minutes to note this down. Well done, sir. Then we move on and we write officially the heading as Q value. No, the heading is already written as Q value. If someone asks you, what do you mean by Q value? What will you say? What is Q value?
The energy absorbed or released
The energy absorbed or released,
during a nuclear reaction.
the energy absorbed or released, a very important point. Lots of students get confused in this Q value. The energy absorbed or released in a nuclear reaction is known as the Q value. Then, if the Q value is less than 0, the reaction is known as endothermic reaction. That means you need energy to be input into the system. This reaction cannot happen on their own because you need to put in some energy inside it. Do we understand this?
Yes, sir.
If the Q value is greater than 0, positive exothermic reaction, it will give out energy. Do we understand this?
Yes, sir.
Everyone understands this?
Yes, sir.
Yes or no?
Yes, sir.
Okay. Now this Q value, you can write it in different ways. The first way you can write it, Q value is mass of the reactants minus the mass of the products. Yes or no?
Yes, sir.
You multiply it by C square, your answer would be in joules. If you multiply it by if you multiply it by 931.5, you will get your answer in mega electron volt. Do we understand this, or this has gone above our heads? Saying bye bye.
Got it.
Or you can write the Q value in this form also. You can write the Q value in this form also. Form number 2, it is the difference between the kinetic energy of the products minus the kinetic energy of the reactants. Yes or no? No or yes?
Yes, sir.
Everyone understands this.
Yes, sir.
The third way in which you can write the same thing is this one. You can write the Q value in terms of the binding energies. In terms of the binding energies, it's summation of the binding energy of the product minus the summation of the binding energy of the reactants. I'll give you 2 minutes to note this down. Then we can see one example of this law of conservation in nuclear reaction. Let us assume that there's a nuclear reaction happening between helium and nitrogen nucleus, and in the end you have oxygen and one proton or hydrogen nucleus. All these are at rest. Let's not bring that motion into picture. So there are three laws that you have to apply. The first law is the law of conservation of mass number. and atomic number, as you can see, the atomic numbers are getting added up and the mass numbers are getting added up. Do we understand this before reaction and after reaction?
Yes, sir.
Second thing you have to apply would be the conservation of momentum. Initially both are at rest, finally both are rest. So 0 is equal to 0, yes or no?
Yes, sir.
So then you have to apply the law of conservation of energy. There is no kinetic energy. So straight away you can find out the Q value. Q value will be summation of mass of reactants minus summation of mass of the products. Yes or no? Here there is no change in kinetic energy. So Q value is simply equal to mass of reactants minus mass of products. Do we understand this? Or you can write it as binding energy of the products minus binding energy of the reactants. Everyone gets this? Everyone understands this? So let me present to you a question. We'll do 2 or 3 questions and that would be it. Let us start with this question. And this is a question. The binding energy per nucleon of oxygen 16. This is how questions are framed. This is a question from IIT-JEE of 1995. Now the tougher IITs. As you can see, if you understand the concept, it becomes very simple. The binding energy per nucleon of oxygen 16 is 7.97 mega electron volt, and that of oxygen 17 is 7.75 mega electron volts. The energy in mega electron volts required to remove a neutron from oxygen 17 is how much? I'll give you a minute to, I'll give you 2 minutes, and after that I'll solve the question. So how are we supposed to do this? Let us first write the equation. We have oxygen 17 and I want to remove one neutron from this. So this will become oxygen 16 plus one neutron. And how do I write one neutron? I write one neutron like this. 1 in the numerator tells us its mass number. 0 in the denominator tells us its atomic number, which is 0 because it is chargeless. Oxygen 17 should become oxygen 16 and I should be able to take out one neutron. They're asking you how much energy is required. So basically what they're asking you, my dear friends, is they're asking you the Q value of this reaction. What will be the Q value of this reaction? That will be the binding energy of the product minus the binding energy of the reactant. Yes or no? Binding energy of the product minus the binding energy of the reactants. I hope you understand this. Now, how do you find the binding energy of the product? Binding energy of the product is product is 7 is oxygen 16 and the reactant is oxygen 17. So binding energy of the product minus the binding energy of the reactants, that is what I need to do. To find the binding energy of the product, the product has 16 nucleon. So I have to multiply 16 by 7.97, and then I have to find out the binding energy of the product. Binding energy per nucleon is 7.75. So I have to subtract minus 7.75 multiplied by the number of nucleons, and the number of nucleons is 17. This is what you need to do, and you will get the answer. The answer that you will get, from this will be coming as minus. The answer that you will be getting is minus, I think 4.23. You will have to do the calculations on your own. The answer that you will get will be minus. This minus sign indicates that energy is required to remove the neutron. Energy will not be released. It will not spontaneously become O17, will not spontaneously become O16. You will have to give in it this much of energy. A very important question to understand the importance of Q factor. I hope you have understood this. I'll give you 2 minutes to note this down. Let us now try to find out the binding energy of helium, so that you also understand how do you find out the binding energy. The mass of neutron and proton are given. You'll have to multiply, divide. Neutrons and protons combine to form helium nucleus. You must understand that a helium nucleus has two protons and two neutrons. Two protons and two neutrons come together to form the helium nucleus. The mass of the helium nucleus is given as 4.0015 mu. What is the binding energy of the helium nucleus? And I will give you 2 minutes to do this. So, bache, how are we supposed to find this? Well, first of all, let us write the equation. Two hydrogen H1 H1 2H1 2H1 will combine to form your helium 41, and we normally write Q value like this, plus Q. Now we just have to find out the Q value of this reaction. Remember, the Q value of this reaction is binding energy of the products minus the binding energy of the reactants. Now you just need to put the values. Q value will be binding energy of the product. Which I think I started doing the next question that I was looking at. We have to find out the binding energy of the nucleus from the mass of the proton and neutron. So basically, sorry, in this case, you have to find out the binding energy of the nucleus. So this will be 2 times the mass of the proton plus 2 times the mass of the neutron minus the mass of the nucleus, and everything is given in AMU. So you just multiply it by 931.5 mega electron volt. You just have to put the values, multiply and divide. This is how it is goes. 2 times the mass of a proton is 1.0087. So you have to be very precise with your calculation. Plus 2 into 1.0073 minus the mass of the nucleus will be 4.0015, and you will see this will be multiplied by 931.5. You will see here that the energy of the reactants is more than the energy of the products, and therefore energy would be released, and the Q value of this reaction, if you want to find out, will be coming as positive. The binding energy, the answer that I have is coming as 28.4 mega electron volt. I hope everyone has understood this. I'll give you 2 minutes to note it down. Well done. Then this is the question actually which I started to solve. That was the next one. The binding energy per nucleon of deuteron and helium nucleus is 1.1 mega electron volt and 7 mega electron volt. This question has come multiple times in multiple exams, and I don't see any reason why this cannot come in the next session. I'm also not seen all the questions of nuclear physics. Maybe this already came in your previous session. If two neutron nuclei react to form a single helium nucleus, what is the energy released? Look at these terms they are using. The first question that we did was how much energy is required to remove a neutron from oxygen. Now they are using the term energy release that will give you a sense of what the Q value would be. Energy release means Q value is positive. Energy required or absorbed means Q value is negative. That is what you will get. I'll give you 2 minutes to solve this question. So how are we supposed to write it? We will first write the nuclear reaction. This was the question that I started off. 2H1 plus 2H1, I hope this time is the correct question, will give us helium 42 nucleus plus the Q value is written like this. You must understand that this Q value will be given by the binding energy of the products minus the binding energy of the reactants. And as you can see here, for the product is one helium nucleus. Binding energy is given per nucleon is 7 mega electron volt. There are 4 nucleons, so 4 into 7 minus the binding energy of a single deuteron is 2 into 1.1, and then there are two deuterons, so 2 into 1.1 into 2, that will give us the Q value for this reaction, and you will see that the Q value of this reaction is coming positive. And this is why, and this is how two deuteron will always try to become helium. Nuclear fusion we call it, and this is the reaction that is happening inside your sun, which is the source of the energy of the sun. And in just one reaction with just two deuteron becoming one helium, you have a tremendous amount of energy being generated, and that is what scientists of these days are trying to replicate. They're trying to create fusion reactors, which is free and safe energy. The only problem with this fusion is that this fusion happens at a very, very high temperature. That temperature is only possible at the core of Earth, the core of Sun. That is why this nuclear fusion, we are not able to harness the power from this nuclear fusion. I hope everyone understands this, yes or no? Okay, that takes me for the last question for today's class, and this is a question from one of the IITs. Just to emphasize the importance of the diagram that we have done, this is the question that, and this is how it is framed. The binding energy per nucleon versus mass number curve for nuclei is shown in the figure. W, X, Y, Z are the 4 nuclei indicated on the curve. The process that would release energy is, which process will release energy? I'll give you 2 minutes to give me the answer. Now remember, since I was talking about energy release and I told you energy is only released okay, I think students have disconnected. So what we will do is, since the time of the class is going to get over, we will discuss this class tomorrow. We'll discuss this question in the class tomorrow. So I'll see you there. Take care. Have a nice day. Bye bye.